Hello, everyone, and welcome back. I am Dr. Supradip Das, Assistant Professor at the Department of Design, IIT Guwahati, and this is the 27th lecture of the course Introduction to Toy Design. In today's lecture, we shift from creativity to economics, but not in a restrictive way. We are going to understand how costing is not a finance department issue but a design decision framework. You will first learn why costing matters in toy design. We will clearly distinguish types of costs and understand how manufacturing processes influence economic structure. You will see how tooling, scale, and overhead allocation change unit cost dramatically. We will examine how assembly complexity, packaging decisions, and compliance testing influence pricing viability. Then we move into the supply chain to understand distributor margin and retail markup. After understanding cost structures, we will explore pricing strategies, cost plus, value-based, competitive, penetration, and premium. And finally, we will apply all of these to some case studies. By the end of this lecture, you should not simply understand costing. You should be able to think economically as a designer. You should be able to look at any toy and ask, what are the likely direct costs? What are the indirect costs? What influences labor costs? You should be able to mentally break down an MRP into retail margin, distributor margin, and manufacturer share. You should understand how scale changes unit economics and when certain processes make sense versus when they do not. You should be able to evaluate whether a pricing strategy aligns with production volume. You should recognize when a product follows a mass market model versus a niche contribution model. You should understand how packaging, logistics, and compliance testing silently influence price. Most importantly, you should be able to design with economic awareness. Not design first and calculate later. You should be able to make material, form, and process decisions knowing their financial consequences. Because design decisions ripple economically across supply chains, and once you see cost behavior clearly, you gain control over feasibility. When we think about toy design, we often begin with creativity, form, play value, and interaction. But every single design decision you make has an economic consequence. Changing the material, adding a sound chip, increasing thickness, or adding one more component all contribute to cost changes. If we ignore costing, we risk designing objects that cannot be produced, distributed, or purchased. A toy that cannot reach children is not successful design. Cost influences scale. It influences durability. It influences packaging. It influences whether the toy becomes inclusive or exclusive. The question is not how cheap can we make it, The question is, how do we design intelligently within constraints? Cost is not the enemy of design. It is one of its most powerful boundaries. One of the most common misunderstandings is assuming cost and price are the same. They are not. Cost is what it takes to produce the toy. Materials, labor, tooling, packaging, compliance. Price is what the consumer sees on the shelf. Between the cost and the price, there is an entire ecosystem. Distributors take a margin, retailers take a margin, marketing adds cost, logistics adds cost. For example, if a toy sells for rupees 1000 in a store, the manufacturer may receive only 400 to 500. That means your design must be viable within that lower number, not the final MRP. Price also communicates value perception. Higher price may signal quality, a lower price may signal accessibility. As designers, we influence cost through design decisions and price through perceived value. Understanding the difference gives you control. Before we price anything, we must understand what we are actually paying for. In toy manufacturing, costs are not just material plus labor. They are layered. Broadly, we divide costs into direct and indirect costs. Direct costs can be traced directly to a specific toy unit. Indirect costs cannot. We also classify costs by behavior. Some costs remain fixed regardless of production volume, like rent or machine depreciation. Others vary directly with units produced, like plastic, resin, or packaging. Then there are semi-variable costs. For example, electricity that increases with machine use but also has a base charge. One of the biggest mistakes young designers make is assuming material cost determines price. It does not. In modern automated factories, overhead often forms a large portion of total cost. And here is where it becomes interesting. As scale changes, cost behavior changes. A toy that is expensive at 500 units may be inexpensive at 50,000 units. Costing is not static. It moves with volume, complexity, and manufacturing structure. Direct costs are the easiest to understand. These are costs you can physically assign to one toy. If your toy uses 120 gram of ABS plastic, that plastic is a direct cost. If it has 4 screws, those 4 screws are direct costs. If it has printed instruction sheets inside the box, that print cost is direct. Direct labor is also included the time workers spend assembling, painting, or finishing the toy. For handcrafted toys, labor may dominate. For automated toys, materials may dominate. Packaging is often overlooked, but box printing, blister packs, and inserts are all direct per unit costs. Direct costs scale linearly. If you double production, direct costs roughly double. But here is the catch. Direct cost is rarely the biggest distortion in pricing. Overhead often is, which brings us to indirect costs. Indirect costs, also called manufacturing overhead, are the silent cost drivers. These are costs that support production but cannot be traced to one specific toy. For example, the factory building where your toy is assembled, that rent must be allocated across all products. The machine used for injection molding, its depreciation must be allocated. The quality supervisor inspecting products, their salary is overhead. This distortion affects pricing, decisions, and profitability. As designers, when you increase complexity, you are not just adding features, you are increasing overhead intensity. Design complexity has cost consequences. Now we move to hidden costs, the ones people rarely think about. Before a toy even enters production, tooling must be developed. Injection molds can cost lakhs or even crores, depending on complexity. Then comes safety testing. Toys must comply with standards: BIS in India, ASTM in US, and CE in Europe. Testing is not free. It requires lab fees and time. Certifications, compliance, documentation, and packaging regulations all add costs. Then logistics come in. Shipping containers, warehousing, distribution margins, and let's not forget retailer margin. A toy selling at rupees 699 retail does not mean the manufacturer gets rupees 699. Retailers may take 30 to 50%. These hidden costs do not appear in your material list, but they influence final pricing dramatically. Designers must see all full ecosystem. The manufacturing process you choose fundamentally determines cost structure. Injection molding has a high initial tooling cost, but a low per unit cost at scale. Hand assembly has a low initial investment but high labor cost per unit. Electronics assembly requires quality testing stations, increasing overhead. CNC cutting wood is flexible but slower. Die cut cardboard is fast but requires dies. Each process has setup time, scrap rate, labor requirement, maintenance cost. Highly automated factories have higher overhead due to machine depreciation. So when you design a toy with integrate interlocking parts, you are increasing mold complexity, assembly time, and inspection stages. Manufacturing is not neutral, it is economically active. Tooling is one of the biggest financial decisions in toy manufacturing. An injection mold can cost anywhere from 5 lakh to 20 lakh or more depending on size and complexity. The cost is paid upfront. Now, here is the important concept: amortization. If your mold costs 10 lakh and you produce 10,000 units, that's rupees 100 per unit just from tooling. If you produce 1 lakh units, tooling cost drops to rupees 10 per unit. This is why scale matters. Design for manufacturability becomes critical. Reducing part count reduces mold complexity. Combining components reduces assembly stages. Aesthetic decisions affect tooling cost. One extra undercut in design may require complex sliding crores in the molds, increasing cost dramatically. Tooling decisions are design decisions. Scale transforms cost. Fixed cost such as rent, machines, and tooling remains the same whether you produce 500 units or 50,000 units. But when you spread them across more units, per unit cost drops. This is called fixed cost dilution. Bulk purchasing reduces raw material cost. High production volumes justify automation. But there is a balance. If you overproduce and demand is low, inventory holding cost rises. Modern automated factories often have high overhead structures. That means they require scale to be profitable. So, when you design a niche toy for 2000 units, you must consider whether injection molding even makes economic sense. Scale is strategic. Design scale decisions determine variability. Assembly is where design decisions become physically expensive. A toy may look elegant on paper, but the moment it reaches the production floor, every additional component, screw, wire, or decorative element become a time commitment. Time in manufacturing is directly tied to cost. Imagine two toys. One consists of two molded halves that snap together with an integrated locking mechanism. The other has 6 molded parts: a battery compartment, internal wiring, 4 screws, and a decorative faceplate that must be aligned manually. The second toy requires more assembly stations, more skilled labor, more inspection checks, and more opportunities for error. Even if the material cost difference between the two toys is small, the assembly cost difference can be significant. Assembly time is often measured in seconds per unit. If a simple toy takes 40 seconds to assemble and a more complex one takes 2 minutes, that difference scales dramatically at production volumes of 50,000 units. Longer assembly time reduces output. Fewer units per hour means factory rent, supervisor salaries, electricity, and machine depreciation are distributed across fewer products. This increases per unit overhead allocation. In other words, complexity increases indirect cost even if direct cost remains stable. Fasteners are another hidden cost driver. Each screw is inexpensive individually, but the labor time required to insert and tighten it adds up. Multiply that by thousands of units, and the economic effect becomes clear. Snap fit mechanisms eliminate hardware and reduce labor, but they demand careful designs. Poorly designed snap fits increase breakage during assembly, leading to rejection and rework. Rework is one of the most expensive outcomes in manufacturing because it consumes time without producing new output. Error rates matter deeply. A design that requires precise wire placement inside a small cavity may increase defect rates. Even a 5% rework rate significantly raises costs because it consumes labor twice. Assembly-friendly design reduces not only time but also risk. Manual assembly versus automation is another decision point. If the design allows automated insertion or robotic handling, labor cost decreases, but tooling and equipment investment increases. If the design requires delicate manual alignment, automation may not possible, keeping labor cost high. Assembly complexity is therefore not just about how many parts exist. It is about how long it takes to transform those parts into a finished toy, how often errors occur, and how much factory infrastructure must support the process. When designers reduce part count, simplify joining mechanisms, and think about assembly flow early, they are not just making production easier, they are directly controlling cost structure. Every second in assembly becomes rupees in pricing. Packaging is often treated as an afterthought in toy design, but economically it is anything but secondary. The moment you decide the size and structure of your packaging, you are influencing material cost, shipping cost, storage cost, and even perceived value. Considering something as simple as box dimensions, if you increase the height of the box by just 2 centimeters to make the toy look more premium on the shelf, you may reduce the number of units that fit inside a master carton. That directly increases freight cost per unit. When toys are shipped internationally in containers, volume becomes more expensive than weight. A slightly bulkier box could mean thousands of rupees more in shipping across a production run. Printing decisions also have layered consequences. A full color offset printing box with matte laminated and spot UV feels luxurious, but it costs significantly more than a two-color corrugated carton. If you add metallic ink or embossing, that requires additional processes and setup charges. Blister packaging introduces another mold, a thermoformed plastic cavity that must be designed, tooled, and tested. That is tooling cost again. But now in packaging, internal inserts add protection, but they also add cost and assembly time. A molded pulp insert is more sustainable than plastic, but it may increase unit cost. If your toy contains delicate components, you may need layered protective materials, increasing both material and packing labor time. Sustainability choices complicate this further. If you choose plastic-free packaging, you may need structural reinforcement in the cardboard to ensure durability. That thicker board increases material cost and shipping weight. However, that same sustainability decision may allow you to position the toy at a higher retail price due to brand perception. Packaging decisions influence far more than aesthetics. They influence logistic efficiency, damage rate during transit, earlier retailer shelf space allocation, and ultimately pricing strategy. A compact, efficiently designed package can reduce freight, reduce storage space, and lower breakage. That efficiency directly improves margins. On the other hand, oversized packaging designed only for visual drama may inflate costs invisibly across the supply chain. So, packaging clearly is a financial design decision wrapped around the toy. So, clearly, every design decision you make has a cost ripple effect. Start with the number of components. A toy made of 3 snap fit parts is very different from one made of 18 screws, 6 inserts, and 2 electronic boards. More parts means more molds, more assembly steps, more inspection points, and more packaging complexity. Material choice matters. Switching from ABS to food-grade silicone changes not only raw material cost, but also molding cycle time. Longer cycle times reduce output per hour, increasing overhead allocation per unit. Tolerances matter. If you design tight mechanical interlocks, manufacturing must maintain precisions. That means better machines, slower production speeds, and higher rejection rates. Surface finish decisions also cost money. A matte textured mold requires surface treatment. High gloss finish may increase polish time. Metallic paint, that adds a full additional spray time. Electronics too have an added cost. The moment you add a PCB, you introduce soldering station, quality testing rigs, failure rate risk, compliance testing, and packaging production. Even modularity affects cost. A modular STEM kit may feel educationally rich, but multiply interchangeable parts, increase tooling, storage bins, SKU complexity, and logistic management. Design complexity increases activity levels, and activity increases overhead allocation. So cost is not something you calculate later. It is embedded inside form, material, and interaction. Testing and certification are non-negotiable in toy design. In India, BIS certification is mandatory. Testing includes drop test, small parts choking tests, sharp edge checks, chemical toxicity testing, flammability tests, and electrical safety for electronic toys. Each testing cycle costs money. Lab fees, documentation, and retesting if failure occurs. Now consider complexity. A wooden block toy may require minimal testing. An electronic talking doll requires battery safety testing, wiring safety, electromagnetic compliance, and sound level testing. Each additional feature increases testing requirements, increasing direct cost. Also remember, failed testing means redesign. Redesign means tooling modification, which is extremely expensive. Testing cost is part of manufacturing overhead. So when you add blinking lights or rechargeable batteries to a toy, you are not just adding delight, you are adding compliance, complexity. Safety is ethical, but safety also has cost implications. Smart designers anticipate certification requirements early in the design phase. Once a toy leaves the factory, it does not go straight into a child's hand. It enters a supply chain, and every step in that chain adds cost. After manufacturing, the toy must be packed into cartons and transported, sometimes across cities, sometimes across countries. Freight is charged either by weight or by volume. And toys, because of packaging, are often charged by volume. If your packaging design is inefficient, you are increasing freight cost before the toy even reaches a warehouse. From freight, the toy moves into storage. Warehousing costs include space rental, handling, labor, and inventory management systems. Toys are seasonal products in many markets, so storage duration can significantly affect cost. Then comes distribution. Distributors buy from manufacturers and sell to retailers. They manage regional logistics, relationships, and stock movement. They take a margin for this service. Finally, the toy reaches retail. Retailers demand shelf space fees, promotional budgets, and margins. The longer the supply chain, the more layers of margin are added. For example, a toy manufactured at rupees 300 may incur rupees 30 to 50 in freight and warehousing before reaching a distributor. The distributor may add a margin of 10 to 20%. By the time it reaches retail, the economics have already shifted. Supply chain is invisible to the child, but central to pricing strategy. If you design a toy for e-commerce direct to consumer, your supply chain shortens and margins shift. If you design for large retail chains, your margin structure changes entirely. Design scale, packaging efficiency, and distribution model are deeply connected. Retail markup is often the most surprising element for designers. Retailers typically operate on margins between 30 to 50%, depending on category and negotiation strength. That means for our rupees 1000 MRP, the retailer may retain rupees 300 to rupees 500. Why such a high margin? Because retail carries risk. They invest in physical store space, staff salaries, utilities, inventory risk, and marketing displays. If a toy does not sell, the retailer absorbs part of that loss. Large retail chains often negotiate aggressively. They may demand promotional discounts, seasonal markdown participation, or exclusive packaging versions. All of these influence cost planning. For designers, this means you cannot design based on MRP. Retail markup directly influences your design feasibility. You must design based on the X factory price, the amount the manufacturer receives after distributor and retail margins are removed. Between the factory and the retail shelf sits the distributor, the intermediary who ensures products reach regional markets efficiently. Distributors manage warehousing at a regional level, coordinate transport to individual stores, handle invoicing, and sometimes even assist in merchandising. For this, they take a margin, often between 10 to 20% of the selling price, to the retailer. This is why direct to consumer brands are growing. By eliminating distributors and selling online, companies can retain a large portion of revenue. However, this shifts marketing and logistics responsibilities back to the manufacturer. Distribution structure shapes pricing freedom. If your toy is meant for large physical retail chains, margin expectations must be built into your cost planning from day one. So, if you want your toy to retail at rupees 1000 and retail margin is 40%, the retailer keeps rupees 400. That leaves rupees 600. If the distributor margin is 15%, that is another 150 removed. For the distributor, that difference of rupees 150 covers their operational costs and profit. The manufacturer now receives rupees 450. That 450 must cover direct material costs, labor, packaging, manufacturing overhead, tooling, amortization, certification testing, logistics to the distributor, and profit. That rupees 450 must cover direct material costs, labor, packaging, manufacturing, overhead, tooling, amortization, certification, testing, logistics to the distributor, and profit. If the actual production cost of the toy is rupees 380, the remaining rupees 70 must sustain the business. That rupees 70 funds design development for the next toy, absorbs direct risk, and contributes to profit. Now imagine if your design decisions increased manufacturing cost by rupees 50, that reduces profit margin dramatically. Suddenly the business becomes unstable. This breakdown explains why companies obsess over small cost reductions. Saving rupees 10 per unit at 50,000 units means 5 lakhs saved. When designers design toys without considering this chain, they often create beautiful but economically impossible products. Pricing is not arbitrary. It is the result of layered cost structures across the supply chain. Up to this point, we have discussed how cost accumulates through materials, assembly, packaging, overhead, and supply chain. But pricing is not just about recovering cost. Pricing is a strategic decision. Price communicates positioning. A toy priced rupees 299 sends a different message than one priced at rupees 2000 to rupees 2999. One suggests accessibility and impulse purchase. The other suggests durability, depth, or premium value. Price determines your audience. A low-priced toy may reach mass market families. A higher-priced therapeutic toy may target clinics, educators, or specialized parents. Price also influences perception. Research consistently shows that consumers associate higher price with higher quality even before interaction. So pricing is not just arithmetic, it is also positioning in market. So the key question becomes, are you pricing to cover costs, to capture values, to compete, to enter a market, or to signal premium status? That's where pricing strategies come in. Cost plus pricing is the most straightforward approach. You calculate total production cost per unit, add a desired profit margin, and set the price accordingly. For example, if your total cost per unit is rupees 400 and you want a 25% margin, you price the product at rupees 500 before distribution and retail margins. This method is simple and predictable. It ensures you recover cost and secure profit. However, it has limitations. It does not consider what consumers are willing to pay. It does not consider competitor pricing. It does not account for perceived value. If your toy costs rupees 800 to produce, but similar toys in the market retail for rupees 999, cost plus pricing may make it uncompetitive. Cost plus pricing protects the manufacturer but not necessarily the market position. Value-based pricing does not begin with cost. It begins with differentiation. Instead of asking, what does this cost to make? The company asks, what structural advantage does this product offer compared to alternatives? If a toy delivers a clear functional distinction, for example, a specialized therapy tool that serves a specific developmental need, the pricing flexibility increases. The buyer may evaluate the product against substitutes that are not direct toys, such as therapy sessions or learning tools that shifts price sensitivity. From a financial perspective, value-based pricing allows higher contribution margins per unit. Contribution margin is what remains after variable cost is deducted, and it is what ultimately covers fixed cost and profit. This strategy works when competition is limited or when the product serves a defined need that reduces price comparison behavior. However, the risk is structural. If the perceived differentiation is weak, the higher price cannot be sustained and volume drops. So value-based pricing is not about emotional branding here. It is about pricing power that comes from functional distinction and reduced substitutability. In future lectures, we will examine how consumer perception shapes value assessment. For now, what matters is understanding how differentiation changes margin structure. Competitive pricing means observing the market and positioning your product within an existing price band. If most similar toys retail between rupees 799 and rupees 999, you may choose to position within that range to remain viable. Penetration pricing goes further. It deliberately sets a lower price to enter the market quickly, gain market share, and build familiarity. For example, a new educational toy brand may price aggressively at rupees 499 instead of rupees 699 to encourage trial. Penetration pricing reduces initial margin but increases visibility. However, once consumers anchor to a lower price, raising it becomes difficult. These strategies are market sensitive rather than cost sensitive. Premium pricing is not simply about charging more. It is about positioning the product within a specific psychological and market space. When a toy is priced significantly higher than competitors, it communicates intention before interaction. A rupees 2,999 wooden open-ended play set sends a very different message than a rupees 399 plastic counterpart. Even before touching the toy, the parent assumes durability, educational value, and perhaps ethical production. Take the example of Montessori-inspired wooden toys made from sustainably sourced hardwood. The raw material cost may not be dramatically higher than plastic alternatives, but the finishing quality, sanding precisions, child-safe coating, and brand storytelling elevate perceived value. The higher price is not only covering cost, it is reinforcing a philosophy of mindful play. Consider also limited edition designer toys or character collectibles. These may use similar materials to mass market versions, but scarcity and brand association create premium positioning. The consumer is not just buying the object, they are buying identity, affiliation, and exclusivity. Another example is therapy-focused or STEM innovation kits. A robotic learning kit priced at rupees 4,999 is not being evaluated purely by material weight. It is evaluated by perceived transformation. Will this improve my child's skills? That perceived developmental return justifies higher pricing in the minds of consumers. Sustainable toys often operate in this space as well. If a company invests in biodegradable materials, fair labor practices, and plastic-free packaging, the production cost increases. Premium pricing becomes a way to sustain ethical commitments while maintaining viability. However, Premium pricing demands consistency. If the toy feels fragile, poorly finished, or visually inconsistent, the price becomes unjustifiable. Premium pricing magnifies scrutiny. It also narrows audience. Higher price reduces reach but increases margin per unit. This strategy works best when brand trust, material quality, and storytelling align clearly. So, premium pricing is not greed. It is a deliberate signal. It says this toy stands for something beyond basic functionality. The key design question becomes, does the product truly embody the value it claims at that price? Because in premium markets, perception and integrity must align. Market positioning from a pricing perspective is fundamentally about scale and margin behavior. A mass market toy is designed for high production volume. High volume allows tooling cost dilution, bulk material discounts, and lower per unit overhead. Because production cost reduces at scale, pricing can remain competitive while maintaining acceptable margins. In contrast, a niche toy operates at lower production volume. Tooling cost is spread across fewer units. Material discounts may be limited. Overhead per unit is higher. To remain viable, margin per unit must increase. This creates two distinct economic models. Mass market models depends on velocity and turnover. Niche models depends on contribution per unit. Neither is superior. They reflect different strategic decisions about scales, risk, and capital investment. It is important to note that we are discussing positioning here from a structural and economic standpoint. In upcoming lectures, we will explore how consumer segmentation, brand identity, and shopping behavior influences which positioning strategy works in the marketplace. For now, what matters is this: your pricing structure must align with your production scale. The economic model precedes the marketing narrative. Let us examine two products that appear to serve the same play theme: pretend kitchen play. One retails at rupees 299 in a mass market toy store. The other retails at rupees 6,999 in a premium children's lifestyle brand store. Both are kitchen sets. Both allow play. Both include utensils and cooking elements. Yet, the price difference is over 20 times. The questions we are not asking is which is better. The question we are asking is, how do cost structure, manufacturing decisions, and pricing strategy create such divergence? We will break this down systematically. Materials, assembly, tooling, packaging, scale, distribution, and margin model. The rupees 299 kitchen set is typically made from thin injection molded polypropylene or ABS plastic. These materials are inexpensive per kilogram. When molded in high volume, per unit material cost drops significantly. Thin walls reduces plastic use. Bright color is added during molding, eliminating secondary finishing steps. Tooling cost for injection molding may be high initially, but when spread across tens of thousands of units, tooling amortization per unit becomes minimal. In contrast, the rupees 6,999 wooden set likely uses solid wood, possibly beech or rubber wood. Wood is more expensive per unit volume than plastic. It also requires cutting, sanding, shaping, and finishing. CNC machining is slower than injection molding cycles. Manual sanding and finishing increases labor time per unit. Unlike plastic, wood cannot be molded instantly into multiple shapes at scale. Production rate is slower, which increases overhead allocation per unit. Material and process already create radically different cost structures. The plastic set is typically designed for rapid assembly. Many parts snap together, fasteners are minimal, assembly may take under a minute per unit in optimized production lines. High output means factory rent, supervisor salaries, and electricity are spread across many units, lowering per unit cost. The wooden set requires component joining, possibly gluing, pegging, screwing, and careful alignment. Surfaces must be checked for splinters. Edges must be smooth. Finishing may involve water-based non-toxic paints or sealant application, which requires drying time. Drying time slows production cycle. Manual labor increases cost per unit. Lower output increases overhead allocation per unit. Time difference multiplies cost difference. The plastic kitchen set is designed for mass retail chains. Production runs are large. Tooling cost is spread across tens of thousands, sometimes hundreds of thousands of units. If a mold costs rupees 10 lakhs and 1 lakh units are produced, tooling adds only rupees 10 per unit. The wooden set likely operates at much smaller scale. If 5,000 units are produced in a year, fixed costs are spread across fewer units. Lower scale means less bulk material discount, less logistic efficiency, and higher storage cost per unit. Economies of scale are not available at the same magnitude. This alone creates large price divergence before branding is even considered. The rupees 299 toy is typically sold through mass retail channels or wholesale markets. Retail margins may be tight, but volume is high. Blister packaging is inexpensive and compact. Multiple units fit into cartons. Shipping efficiency is high. The rupees 6,999 product is often sold through boutique stores, concept stores, or direct to consumer online platforms. Packaging is heavier, more protective, and often aesthetic. Shipping cost per unit is higher due to weight and box size. Retail margin may also be higher in premium stores. Channel selection shapes final price. Let's construct a simplified illustration. For the rupees 299 toy, manufacturing cost might be around 120 to 150 or maybe less than that, including plastic, labor, overhead, and packaging. After distributor and retailer margins, the manufacturer may earn a small per unit profit, but high volume compensates. For the rupees 6,999 toy, manufacturing cost could range from 2,000 to 2,500 due to material, labor, finishing, and lower scale. After margins, the remaining contribution per unit is much higher than the plastic set. The plastic model depends on selling thousands of units quickly. The wooden model depends on a strong margin per unit at a lower sales volume. Both are economically valid but structurally different. The rupees 299 kitchen set likely follows competitive pricing. Its costs remain within an expected market band to compete with similar products. Margin per unit is low. Volume drives sustainability. The rupees 6,999 kitchen set follows premium pricing. It accepts lower volume in exchange for higher per unit margin. It may also use value-based pricing. If differentiation justifies price, neither is random. It may also use value-based pricing if differentiation justifies price. Neither is random. Each aligns with its production scale and cost structure. Now let us examine a category where the material composition is broadly similar, yet pricing differs dramatically. Foam dart blasters. Hasbro's Nerf entered the Indian market as a global brand leader. Nerf products were positioned at premium price points, often retailing between rupees 1,999 and rupees 4,999. Soon after, smaller local manufacturers began offering visually similar foam blasters priced between rupees 399 and rupees 999, something like this. The core material in both cases is plastic injection molding, inspiring mechanisms, and foam darts. The material category is not radically different, yet the price gap is substantial. This case helps us understand how penetration pricing operates when smaller competitors attempt to undercut a market leader. Some financial figures discussed will be hypothetical but structurally realistic. At first glance, both Nerf and local foam blasters use similar raw materials. ABS or polypropylene plastic bodies, simple spring mechanisms, molded components, and lightweight foam darts. However, cost behavior differs. Hasbro operates with high-quality resin specifications, tighter tolerance models, tighter tolerance molds, better finishing, and stronger durability testing standards. Tooling precision and mold finishing significantly increase initial investment. Local brands often reduce wall thicknesses, simplify internal mechanisms, and use lower grade resin to reduce cost. Production scale also matters. Hasbro may produce globally in massive quantities, but imported goods carry freight, customs duty, and regulatory compliance costs. Local manufacturer may produce domestically, eliminating import duties and reducing logistics costs. Materials similarity does not imply cost equivalence. Quality standards and supply chain structure change cost behavior. Hasbro invests heavily in R&D, safety testing, performance testing, and brand-specific design engineering. Product innovation includes new firing mechanisms, rotating barrels, motorized components, and safety compliance across multiple countries. These development costs must be recovered through pricing. Local brands often reverse engineer basic mechanical concepts. Innovation investment is lower. Tooling may be simpler. Molds may not require the same durability life cycles as global brand molds. Lower development cost reduces financial recovery pressure. Penetration pricing becomes viable when development investment is minimal. Hasbro products entering India often incur import duties. International freight, warehousing, and multi-layer retail margins. Each layer adds cost before the product reaches the shelf. Local brand manufacturing domestically avoid import duty. Freight is local. Distribution may happen through wholesale markets rather than premium retail chains. This shortens the cost chain. If a Nerf blaster lens at rupees 1,200 ex-factory, import cost margin stack up to reach rupees 2,999 retail. If a local brand manufacture at rupees 250 to 300 per unit domestically, even after margins, the product can retail at rupees 599 to rupees 799. Supply chain compression enables penetration pricing. Hasbro's Nerf operates under premium pricing. The brand carries global recognition, performance reliability, and perceived safety assurance. Pricing reflects development investment, brand equity, and global positioning. Local brands use penetration pricing to enter the category aggressively. The goal is not brand prestige initially, it is market share acquisition. A rupees 599 blaster lowers entry barrier dramatically compared to rupees 2,999. Parents unsure about category durability or safety may prefer trying a lower priced option first. Penetration pricing allows local brands to capture first-time buyers. Let us assume hypothetically but structurally reasonable numbers. If Hasbro landed cost per unit after import and duties is around rupees 1,200 and the retail price is rupees 2,999, the contribution margin per unit may be significant but must cover global marketing and R&D investment. If a local manufacturer produces at rupees 300 per unit and sells at rupees 699, the margin per unit is lower, but the production cost is drastically lower. Local brands depend on high volume and rapid turnover. Penetration pricing sacrifices per unit margin to accelerate adoption. Penetration pricing carries risk. Thin margins means small increases in material cost or defect rates can eliminate profit. Lower material quality may reduce durability, impacting brand trust. Without differentiation, price competition intensifies and margins compress further. Sustainability requires either eventual scale dominance or gradual brand strengthening. Penetration pricing is an entry point. Penetration pricing is an entry strategy, not always a long-term positioning strategy. This case demonstrates that similar material categories do not automatically produce similar pricing. Development investment, brand equity, import duties, supply chain structure, and strategic intent all influence final MRP. Hasbro maintains premium positioning supported by R&D and brand equity. Local brands used penetration pricing to disrupt entry barriers and captures market share. Both strategies are economically coherent within their respective structures. The lesson is not which is better. The lesson is that pricing reflects structural decisions made long before the product reaches the shelf. Pricing is a reflection of system design. Let us now examine a product that sits at the intersection of toy and technology, the Nintendo Switch. Unlike foam blasters or kitchen sets, this is a complex electronic product. It includes a screen, battery, processor, controllers, wireless components, and software integration. It is also a market leader in the gaming segment. The interesting question here is not simply why it is expensive. The more relevant question is how do costing variables in technology-heavy toys influence pricing decisions? This example will help us understand hardware cost, software ecosystem strategy, and pricing models in high-tech toys. Nintendo invests heavily in research and development, hardware engineering, firmware programming, operating system design, controller innovation, and compatibility testing require multi-year investment. Unlike a physical toy that may require tooling and mechanical testing, this product requires hardware software integration testing. Game ecosystem development also matters. Developer kits, SDK support, and platform stability are part of the investment. These are high fixed costs. Once incurred, they must be recovered across millions of units. The higher the fixed cost, the more important volume becomes. Nintendo produces the Switch at a massive scale. Large production volumes allow better supplier negotiations for chips, screens, and batteries. Assembly lines are automated and optimized for output. Over time, as production stabilizes, defect rates decreases and manufacturing efficiency improves. This reduces per unit cost gradually. Technology products often becomes cheaper to produce over time, even if the retail price remains stable. Scale is essential in recovering fixed development cost. Interestingly, technology companies sometimes price hardware at thin margins. The Nintendo Switch was not priced at extreme premium compared to its hardware capability. In some cases, gaming consoles are priced near cost to accelerate market adoption. Why? Because revenue does not come only from hardware. Game sales, digital downloads, subscriptions, and accessories create long-term revenue streams. This is ecosystem pricing. The hardware price must encourage adoption. Technology-based toys carry additional risk. Component shortages can suddenly increase manufacturing costs. Currency fluctuations affect import-export margins. Rapid innovation cycles mean products can become outdated within a few years. Pricing must therefore balance competitiveness with risk buffer. A low price, too, may leave no protection against supply chain distribution. This case demonstrates that in technology-heavy toys, pricing is rarely simple cost plus. High fixed development cost must be recovered through scales. Hardware pricing may be strategically positioned to grow ecosystem participation. Revenue does not stop at the physical product. Unlike simple toys, technology toys operate in multi-layered cost and revenue systems. Pricing reflects long-term strategic planning, not just manufacturing expense. This example shows that when technology enters toys, cost variables multiply, and pricing becomes systemic rather than product-specific. So today we explored something that often feels invisible in design education, that is economics. We saw that cost is not a restriction but a structure. We understood that price is not just a number on a shelf. It is a layered outcome of manufacturing, distribution, margin, and positioning. We examined how seconds in assembly becomes rupees in pricing. We saw how tooling decisions echo across thousands of units. We realized that packaging size influences freight. We understood that scale can transform cost behavior entirely. And we saw that pricing is not just arithmetic. It is strategic alignment. As designers, you now carry a new lens. When you change a material, you change economics. When you add complexity, you increase overhead. When you reduce parts, you increase feasibility. Costing is not the enemy to creativity. It is the architecture that allows creativity to exist in the real world. As you move forward in your design journey, keep reflecting on the topics we discussed. Let economic awareness guide your creativity and decisions as you continue shaping the future of play. Design boldly, design responsibly, and until we meet again, keep your ideas intelligent, your thinking strategic, and have a wonderful, playful time.